Hi, in this tutorial, I'll explain to you the last analysis that you can do with the GUI. Okay, so simply run the GUI, choose a data set, upload file, this one, driver gene, output images all, output directory, say this one, select folder. And this time you choose Kaplan-Meier after clustering methods on expression. Click done and your code is running. Now, while the code is running, I already outputted the results beforehand. And in this analysis, you will get two Excel tables and you should only look for this one, the one that says k-means and not k-means after PCA. And I'll explain what this table does by looking at graphs. Okay, so what we do here is basically we try to cluster the patients by their gene expression according to different clustering algorithms. And since the lab only knows k-means, we only use k-means. Okay, so, and then we check whether by clustering the patients differently, by different clusters, or whether we get a significant difference between the survivability of the groups. So let's see, for example, here we have 6 groups. Here are 5, 4, 3, and 2. Okay. And if you notice, then in this title, you see Kaplan-Meier patients clustered by k-means after PCA, and in another title, Kaplan-Meier patients clustered by k-means. So I did 2 types of clustering, one that is where the patients were clustered by k-means only, and one where the patients were clustered by PCA, where I did a PCA on the patients and then clustered by k-means. Now, I personally think that there is no need to do an analysis by PCA and then k-means. And I'll explain why in a little bit. Okay, so here's an explanation. Here's a representation of the patients and them being clustered by different number of clusters, like 4, 3, 2. Okay, so in this plot, what you see here is very, very cumbersome, but the reason for that is because I chose a data set or a gene expression table with many, many candidate genes. So this graph is not really clear. And I'll try to show you the graph and how it looks with fewer candidate genes. slides. Yeah, okay, this one. So this is the graph I showed you before. Let's look at this one. It's basically, in this case, there is only a graph for that where we split the patients by 2 clusters. So we take the 2 clusters and which were clustered by k-means, and we, for each gene, we average the gene expression of all the patients in each group. Okay, so in our blue group here, this was the average gene expression, and in the red group, this was the average gene expression, and we compare the results by t-test, which are summed up in our Excel table. Okay, and as I said, please look only at the graph with k-means and not k-means after PCA. So the problem is that sometimes you have too many candidate genes. So I tried to plot to get a different representation of, it's the same calculation, but we chose only certain genes, and I'll show you how and what I mean by that. No, that is one. And not this one as well. This is the Kaplan-Meier. Okay, yeah, this one. So again, this plot might not be too clear. So what I did here is I simply took, you see that group 1 is represented by blue, group 2 is by red, and it's the same bar plot as before, but we only take genes here where their average in group 1, their gene average expression, let's say that MET, yeah, it's a gene. Its average expression in group 1 was below the average expression you simply compare it to its own average. Let's say that the average, I don't know, was 7 gene expression. Yeah, and in group 1, the average of the gene expression of all the patients in MET was, let's say, 6. So so the average in MET in group 1 was below the average of MET in general of all the patients. Okay, so, and in this time, and in group number 2, we took all the genes that had an average expression in above their average with all the patients. Let's say, let's look at again MET in group 2. Yeah, in group 2, let's say that average was 8. So the average expression in MET in group 2 was 8, and it's above the overall average of MET of all the patients, which was 7. let's say. So we get all the genes that in group 1 had here below average expression, but in group 2 had above average expression, okay? So it's a way to filter some genes out. In this case, we had genes that in group 1 had above average expression, and genes in group 2 had below average expression. I know it's confusing. In this plot, we are supposed to see genes in group 1 that have above and genes that in group 2 have above average expression, and we see none. Below we see none. Okay, let's see that if we see a different pattern in a different data set. See, and clustering. Let's see, no, we also see a similar pattern where like above genes, above, I mean, the average in expression in all the patients, you don't see any genes. Okay. Yeah, okay, so there is that. And now, first, I'll also explain about these silhouette graphs. And in order to check whether our clustering was good, we check that with a silhouette graph, and we want to see that there aren't many negative values here. And I think splitting the data by 2 clusters is quite good. And this is done for, here is for 4 clusters, 5 clusters, 6 clusters, etc. Okay, there is one more graph, but I will explain, I will show it later. And now I want to explain a little bit about k-means and what it does. So let's say that we have these points, point number 1, point number 2, 3, and so on. And we want to cluster them. So first, in k-means, we choose the number of clusters that we want beforehand. And let's say that we want 2 clusters. So we output 2 randomly roots or kernels. And let's say that we choose this one and this one. And in advanced algorithms of k-means, we don't choose the points randomly because it can cause problems. And also in high dimensions, k-means doesn't work that well. Okay, so what we do is first we have the 2 roots and we calculate the distance of each data point to our roots, and we want to choose the minimal distance. So point number 1 is closer to, let's say, root A, and this is root B, and point 2 is closer to root B, something like that. Okay, and we get 2 clusters now. So now we calculate new roots. Okay, and the way we calculate the new roots is we simply take the average of all the points. So let's say our average here, it's point A is now here. This is our average, and point B is now located here. Okay. So, and again, we simply calculate the distance, the minimal distance of each data point to the roots, and we associate its data point to the closest root. Point number 1 is closer to this one this time. Point 2 is closer to this, and I think it's closer to this one. And again, we get 2 clusters. We calculate again the new roots. Okay. And this is the average this time. And now I believe this point is closer to this root. These are our clusters. We have 2 clusters, and again, okay, so let's say that point number 3 is closer to this one. Okay, so we got a cluster that is similar to our previous iteration, so we stop our calculation once there is no change in the clusters. And that's basically it. And k-means works on our simply values of the data, and that's it. And now I'll explain a little bit about PCA and why I think it's not necessary in our case here. So the goal of PCA is to represent the data in such a way, in a different base, in different axes, such that we transform the data in different bases, such that the data will look closer, the closest, I'll simply draw it. Yeah. So this is our axis X, and this is our axis Y. And these are our data points. Okay, so You currently, let's look at point number 1. Let's say that in the x-axis, it has a value of 7, and in the y-axis, it has the value of 3. Okay, so we can rotate these bases, axis x and axis y, and we will have our data, but represented in a different base. Wait a second. So we rotate our axis, we get a new x-axis, and we get a new y-axis. Okay, and our value, let's say, in our new x-axis is, this time it's, I don't know, 8. And in the y-axis, it's a -2. Okay, so our data is our data, but its values are on our new rotated axis is different. Okay, so let's say our data is patients and their gene expression. Okay, and let's say that our axis X is gene expression in gene 1, and the axis Y is the expression of the patients in gene 2. Okay, and what we're trying to do is in PCA is actually find a transformation such that in a certain axis, the variance of the data towards that axis will be maximal. And what I mean by that, so the variance is simply the distance towards a certain axis. Yeah, this is the variance towards the x-axis, and you have also the variance towards the y-axis as well. And in PCA, our goal is to rotate our axes in such a way that the variance of the data will be maximal in a certain axis. We first search for one axis and then move on to the other ones. We always rotated axis. Okay, so we found out, let's say that we rotated the data and we find out that this is the maximal variance around our new x-axis. Okay, and this is the best variance that we found. Now, what is the x-axis? It's actually a linear combination of our previous bases, our previous axes, where alpha and beta are simply just scalars or values, you could say, numerical values. So basically, let's say that point one here has a value of, we said 8, so let's say 8. And it's simply a combination between its previous value, which was 2 in the y-axis and or G2, and 7 in the x-axis, which is G1. So basically, our x-axis is a linear combination of our genes, which are bases, basically linear combinations of the gene expression data of the genes of the patients. It's like combining not exactly apple and oranges, but you sort of get a new variance of the gene expression, which is okay. But that depends on what you want to do. And the goal in PCA is, again, to find the maximal variance in a certain axis and represent the data in the new base that we found. And then we simply, then we can reduce a certain base. Why? Because our variance was the greatest in our new x-axis, and we don't gain much knowledge, we don't need our new y tag axis in order to explain the data, explain its variance, show that it's different. We can only use the x-axis. So it's PCA is mainly used to reduce memory, and it's a great tool to reduce the number of pixels used to represent an image. But we have to think what it means to reduce our genes. If we want to explore them, we explore our candidate genes. So what it means to simply get rid of Y tag, which is a combination of both G1 and G2. It's a combination of all our candidate genes. And again, and even so, Y tag is sort of gives us a new representation of gene expression. So what does it mean to represent the data in with different values? We lose the meaning of our data, of our gene expression, which is fine if you want to do certain things. You can cluster the data later on, but you'll have to know that you are clustering on something that's a little bit different than our known gene expression, and also that the goal of PCA is just to, delete this Y tag axis. It's to represent the data in a better base and also to delete certain bases. Do you want to delete your candidate genes? I have no idea. Maybe you do. And because there are some ways to find out, for example, which gene is more contributing to our new X tag axis, but I did not have time to go over that. And another thing, you can also try and think and say, you're probably thinking to yourself, okay, why don't we represent the data with where our x-axis is actual patient 1 and y-axis is patient 2, and our data are simply genes, gene 1, gene 2, etc. And the values are expression of gene 1 and patient 1. But then what? You will represent, you'll get a new base, which is a linear transformation of, or a linear combination of the patients, and then you reduce the amount of patients. You don't want to do that because you want to cluster all the patients into different groups. So you do want to look at a graph like this, where the bases are the genes and the data points are the patients. But again, I don't see what PCA gives us here. And PCA is not a clustering method. It's a way to represent the data differently and perhaps better, but you have to think about the values of the data in that different transformed base, and it also reduces the amount of new bases. And you can choose how many bases you omit, yeah, because we obviously have more than 2 genes and more than 2 patients. So I will take with a grain of salt this buzzword that goes that is quite prevalent in the lab. Okay, and I know I focused on PCA and K-means because these buzzwords are used quite a lot in the lab, and I don't think people quite get what they actually mean. Okay, so now let's go and explain some of the tables. We do have one type of graphs to explain, but let me page layout. Okay, so I'll explain here what you see. So in the first sheet, you see obviously the gene names, and then in column B, you see the average of the gene expression for group 1. This is for MET. In group C, in column C, you see the average expression of the genes in group number 2, and then you see standard deviation for group 1, standard deviation for group 2, standard error for group 1, standard error for group 2, and then p-value of ANOVA and p-value of t-test. Now, I only output tables for 2 clusters, and in 2 clusters, obviously you can do t-test, and then ANOVA and t-test are equal. But if you also put an option for future coders to change it, so you output you'll do an ANOVA test, and you'll get a p-value of ANOVA test. And okay, so in sheet number 2, you get all the patients and their group they belong to. So here you see the patients that belong to group number 1. And soon you will see the patients that belong to group number 2. And sheet number 3 is a little bit confusing. And I'll try to explain. You have to look at trios or trios of of columns A, B, C, D, E, F, etc. So let's look at D, E, and F. So genes table 2, it's basically what it means is we look at the genes that had average gene expression, which was above the overall average in each gene for all the patients. And this is in group 1. And in group 2, they had an average which was below the average in their gene for all the patients. So we have above in group 1, below in group 2, and GHI, you see the genes that had below average in group 1 and above average in group 2, and JKL, it's below and below, and these are empty. And again, in ABC, you have above and above, and these are all also empty. So perhaps we can simply delete those columns. And it's just a different representation. It's the same thing, as in sheet 1. You have the same data in sheet 1, except I just simply took, I did the job of splitting the genes by whether they had an above average in group 1 or below, etc., etc., and what happens in group 2, etc., etc. The last thing that I might want to show you is I also did a Pearson correlation coefficient, and you obviously cannot see the names of the genes because there were too many. And again, Pearson correlation coefficient table, and the number of clusters was 2. I only did that for when the clusters, there were 2 clusters, and this is for group number 2. And the clustering method was k-means only, and this is for group 1. Again, look only for the clustering method, which was k-means after k-means only and not after PCA. And maybe it will be clearer when there are fewer genes. Pearson, it's in B. Yeah, it's clearer here. Yeah. Okay. So this closes the explanation regarding the all the possible analysis that you can do currently with the GUI. And so yeah, that's it.